The title of my presentation is Some Evaluations on Spectrogram Art Communications Exchanging Secret Visual Messages.
Spectrogram art communications convey visual messages drawn on sound signals.
It may be employed as a sort of steganography techniques enabling sub-channel communications in a covert manner.
Spectrogram art communications are expected to transmit visual messages by using speakers equipped in ordinary laptop computers. It realizes near-field communications without advanced wireless radio devices. This picture shows our pilot implementation of a visual communication system that exchanges text messages by using spectrogram arts. Text messages are easily understandable by human users even if some parts inevitably degrade due to undesirable environmental noises. It is because text messages are very familiar symbols to human users. Transmitting such visual messages, we can realize robust communications that are directly understandable by human users without any advanced decoders. This study employs a DFT filtering method to generate spectrogram art signals. This method filters source signals with mask patterns to generate sound signals consisting of spectrogram arts. A white noise is one of the best candidates for the source signals. The mask patterns are the spectrogram arts themselves. Fourier transform and its inverse transform are defined as follows. Filtering a source signal denoted as large X with a mask pattern denoted as large B is equivalent to be the multiplication of these information in the frequency domain. The inverse transform of large Y is a resultant sound signal consisting of a spectrogram art. The DFT filtering method provides two approaches for generating spectrogram art signals. They are named the additive method and subtractive method, respectively. For the spectrogram arts conveying text messages, positive and negative mask patterns may potentially be applicable. Because human users can recognize both patterns without difficulties, the additive method allocates 1 to the text regions of spectrogram arts with negative mask patterns. This slide shows an example of the additive method. On the other hand, the subtractive method allocates 0 to the text regions of spectrogram arts with positive mask patterns. This slide shows an example of the subtractive method. Some experiments were conducted to examine how far the proposed technique conveys the information in a real situation. The inaudible frequency bands over 18 kHz were employed for embedding the text messages. The additive method was only evaluated in the experiments. The distance between the speaker and microphone was chosen at 5 meters, 10 meters, 15 meters, and 20 meters. A high-power loudspeaker covering the inaudible frequency bands was employed. This picture shows the setup of the experiments. This is the spectrogram obtained at the distance of 5 meters. This is the spectrogram obtained at the distance of 10 meters. This is the spectrogram obtained at the distance of 15 meters. This is the spectrogram obtained at the distance of 20 meters. As I mentioned, this experiment employed a high-power loudspeaker. This is why we can still recognize the messages, even if the distance is 20 meters. However, if the power of sound signals decreases, the visibility of the messages must be degraded, as the distance increases. It happens especially in the case of using low-power loudspeakers equipped in ordinary laptop computers. This is the spectrogram obtained in such a situation. As you can see, it is difficult to read the messages due to their low visibility. The distance of spectrogram ART communications depends on the power of sound signals. To keep the visibility of the messages as much as possible, the crest factor of spectrogram ART signals should be reduced. The crest factor is defined as the peak amplitude of a waveform divided by the RMS value. If the crest factor is minimized, the power of each frequency component included in spectrogram ART signals is maximized. As a result, the visibility of the messages increases, as the crest factor is reduced. These are the crest factors of some typical waveforms. The minimum value of crest factors is 1. The crest factor of waveforms with no peaks, such as direct current or a square wave, takes the minimum value. To reduce the crest factor of spectrogram ART signals, this study employs an audio clipping technique, one of the approaches proposed for the crest factor reduction so far. This technique is actually a sound effect named compressor employed in the audio signal processing of music production. A compressor is used for maximizing sound signals. The crest factor of sound signals is reduced by amplifying the sound signals with a compressor. A compressor works with a mapping function that defines the relationship between the input and output signals as shown in this figure. Although such an audio clipping technique reduces crest factor, this nonlinear process inevitably generates unnecessary frequency components, decreasing the visibility of the spectrogram ART signals. Therefore, the proposed technique filters the resultant signals with the same mask pattern employed in the generation of the spectrogram ART signals to reduce such defects. To examine the effectiveness of the proposed technique, a computer simulation was conducted. This figure shows an original spectrogram ART signal without the proposed technique. The crest factor of this spectrogram ART signal is 7.6. This figure shows the spectrogram ART signal after clipping.
The crest factor of this spectrogram ART signal is 1.
Compared with the original one, the crest factor is reduced by the proposed technique. However, unnecessary frequency components decrease the visibility of the spectrogram ARTs. This figure shows the spectrogram ART signal after filtering. The crest factor of this spectrogram ART signal is 3.1. Although the crest factor increases slightly, the visibility of the spectrogram ART signal is improved, compared with the original one. This is a spectrogram ART signal generated by the conventional technique.
As you can see, it is difficult to recognize the message.
On the other hand, this is a spectrogram ART signal generated by the proposed technique.
As you can see, the message is recognizable. The simulation indicates that the proposed technique may potentially improve the visibility of spectrogram ART signals, compared with the conventional one. In order to examine how the proposed technique works, this study conducted an experiment in a real situation. The location was a cafe. This figure shows its layout. Spectrogram ART signals were emitted by two laptop computers each other. These laptop computers were separately located on different round tables. Background music was always broadcasted inside the cafe. The average noise level was about 65 decibel in C-type characteristics of a noise meter. This figure shows the spectrogram arts received at the terminal located at B, while the corresponding terminal was located at A. The distance between the terminals was about 2 meters. It was an example of text chat that the terminal located at A asked the name of BGM, and the terminal located at B answered it. The experimental result suggested that the proposed technique may potentially be applicable to such text chat conversations, if the distance between the terminals is about 2 meters or so. However, the messages became ambiguous when the distance between the terminals increased. This figure shows the spectrogram arts received at the terminal located at I, while the corresponding terminal was located at A. The distance between the terminals was about 6 meters. It was an example of text chat that the terminal located at A asked the name of BGM, and the terminal located at I answered it. The range of the communications apparently depends on the power of speakers equipped in laptop computers. Since laptop computers generally equip lower power speakers less than 1 watt or so, the range of the communications is inevitably limited. Increasing more the distance by using such poor speakers is one of the agendas to improve the capacity of the text chat conversations by spectrogram art communications. Inaudible sound communications are expected to be applied to not only text chat services but also advertisement usages as well. If louder speakers equipped in the public address systems emitting BGM are available, the proposed technique may potentially be employed to broadcast advertisement messages as shown in this figure. Discovering such secret messages might be a motivation for consumers to visit the places. This presentation describes the basic concept of spectrogram art communications, and the results of some pilot experiments. The analysis on the reliability and capacity should be discussed furthermore, by examining how well the proposed technique performs in real situations. Development of a more practical text chatting software for further experiments is one of our agendas.